Welcome back to ECE 442-542. We're getting into the last stretch before the second exam. I know we just had our first exam, but I want you to make sure that you're aware of when exam number 2 is coming on us. Homework number 3 is due on Thursday, then the next Thursday, homework 4, and then the next Wednesday is when our second exam will occur. And I'm anticipating exam 2 will be dealing with inverse Z transforms and discrete equivalents, which is what we're continuing with in today's lecture material. If you didn't look at your email, or if you weren't just really watching the D2L site, you maybe missed a couple of new installments that I generated on whenever it was, Friday or Saturday, sometime they got posted, and that is concerning zero-order Hold equivalence of state space. How do we go from a continuous time state space representation to a zero-order Hold equivalent? And those are lectures 4.3a and 4.3b, the B being a numerical example or an illustration of that. And actually in the B part, I actually try to develop some equations of motion for a mass spring damper system. So we're going away from ECE in that particular second order system, draw or sketch the all-integrator block diagram. That immediately gives us our state space representation in continuous time, and then we proceed to finding numerically what that second order, zero order Hold equivalent discrete time system looks like. We will, in a sense, go over that very quickly in this summary of the zero order Hold equivalents, and I've created a square to give you a way to visualize what you're doing, or how to maybe orient yourself when we're talking about finding these discrete equivalents, and in particular using the zero order Hold, which means that we're preceding this transfer function with the zero order Hold. Today we will not be doing that. Today's discrete equivalents will be via numerical integration. I'm hoping we can get through all of that, and then maybe the next time we will talk about another discrete equivalent approach, which is by means of pole zero mapping. That's the plan for moving forward. This is too wide, but there's 4 boxes here, and this is the summary square of the zero order Hold equivalent. We have in the leftmost column continuous time and the rightmost column discrete time. The top row is time domain material or information or a model, and the second line is the frequency domain. I'm going to then slide over, if you now know that the top is time and the bottom is frequency, in a way of trying to capture this idea of how do we go from continuous time to discrete time. And we can do it many different ways. We could start with a continuous time state space representation, which I'm calling script S sub C. We could put a zero order Hold at the input, which means hold the input constant for one sample period at each sample period, and that produces a discrete time state space representation. Meaning, if you had an X vector that contained position, velocity, voltage, current in the continuous time system, you would have the same meaning to those variables or components of your state vector on the discrete time system. They would now be corresponding to position, velocity, voltage, and current, if that's the order that I had them before. You can see that the output equation goes across unchanged or unaltered in this description. You also should be comfortable finding the transfer functions from the discrete time representations, capital G of S being this C times Si minus A inverse times B plus D, or you could do that on the discrete time side and Z transform those state equations and end up with C Zi minus phi, that matrix inverted, times gamma plus D. Or, given this G of S, you could find the G of Z from this zero order hold formula that we talked about in class. Some of these we've talked about in our pseudo class that was held on Friday. And you'll want to maybe look at those videos or those notes to better appreciate this top row transition from the left column to the right column. How do we find this phi matrix and the gamma matrix? The phi matrix is actually just a matrix exponential, e to the a capital T, where capital T is our sample period. Or if we were doing this by hand, you could find Si minus A inverse as a matrix. That's going to be some matrix with S's all over the place. You could inverse Laplace transform each of those element entries in this 10 by 10 matrix. Oh, we said we could do 12 by 12. Whatever your A is, that's now this Si minus A inverse matrix. That will be a function of little t time, but if you replace that little t with capital T, you now have another way of thinking about e to the a capital T. And I talk about this in those virtual lectures that were given on Friday. Nobody showed up. Never mind. I was hidden away in my office trying to capture that material, and the computer actually didn't cooperate very well, so you'll have to see what happens when it just starts spinning. The Windows blue spin of death occurred. And then I forgot to turn my mic on and off, and well, you can have a good laugh at that. The input matrix, since I was really laughing at that point, but gamma now is our input matrix in the discrete time setting, and that's simply taking this matrix exponential where mu is a variable and integrating that with respect to mu, and that gives us now our input matrix gamma. That I'm assuming you know or will know by homework 4 and exam number 2. This square, how to navigate around this square of going from continuous time to discrete, state space to transfer function, etc. Now, to set this, that was the zero order hold equivalent approach to finding discrete equivalents. Let's just remind ourselves of this, what we can do with discrete equivalents. We really have two different scenarios. Here's the analog block diagram up top and the discrete block diagram down below. We have been, up to this point in the semester, focusing on the zero order hold equivalent, which means we have some system that's preceded by a zero order hold, and then we combine those, knowing that they were going to be there all along. Let's just incorporate that, the dynamics of the zero order hold, into the G of S and find the combined G of Z. That's what we've been doing. Today what we want to do is actually talk about a different way of finding a discrete equivalent, and that is let's say that we have already designed a controller. Maybe that's some first order transfer function, which could be a PI controller, a proportional integral controller, and we'll learn more about this as we go. or it might be a PID, maybe it's second order. Or maybe it's not even in a control system, maybe it's just a filter. Maybe this C of S is a Butterworth filter, low pass, 12th order. We want to figure out how do we get a C of Z from that. And this is not preceded by a zero order hold, is it? We want to just directly map a transfer function, C of S, and find its discrete equivalent, C of Z. And I want you to be comfortable with the difference between these different discrete equivalents. What we've been doing so far is finding the zero order hold equivalent. What we're going to talk about today is a slightly different strategy where now we are not preceding that transfer function with a hold mechanism. It wouldn't even have to be a zero order hold. It could be a first order hold, but we've been dealing with zero order holds. We want to find how do we go from C of S to C of Z. That's the idea. All right, now we can start moving at the same pace. That you should be able to just sort of look at after the fact. And now I'm actually going to maybe change the notation a little bit. What we're wanting to do, let me just say that we're starting with some transfer function, capital H of S, which we might have an input signal injected into, producing the Laplace transform of an output. This might correspond to, as I said, maybe a filter, a band pass, a low pass, a high pass, or it might be actually a controller. Since this is the class we're doing, we may be interested in finding the discrete representation or a discrete realization of some analog controller that somebody might have already designed. That's what capital H of S is. Or H of S may not actually be a plant. It may not be some physical systems dynamics that we want to control. So H of S may not be a plant. That's the distinction that we're using. Maybe I shouldn't have made it green if it's not supposed to be a plant. I had a student one time and she said her dad was reading her thesis and he goes, "Amy, why do you keep talking about a plant? I don't see any green leafy thing anywhere in your thesis." Dad. All right, so now what we want to do is maybe not have a green leafy thing. Maybe this is not a plant. It's now a controller or a filter. And we want to produce now a discrete equivalent of that H of S so that now we have this relationship from an input U to an output Y, and I hope that it's clear that if you really need to find Y, you know that it's H times U in the frequency domain. And U might be as simple as a step, and that's maybe something on homework number 3. I might say apply a step input to this system. All right, now let's get our bearings back. This is talking now about discrete equivalents. And now we are concerned with finding a Z-transform transfer function from a Laplace transformed representation, and we are looking really at three different techniques for these discrete equivalents that we are going to be using or talking about in this class. One is what we will say is a class that we'll call numerical integration techniques. Another class of discrete equivalents will be what we will call pole zero mapping techniques. And we've already talked about one of these discrete equivalents, which is a hold equivalent, which maybe I'll just say in general it could be a hold equivalent. We've actually specialized that to a zero order hold equivalent. But now we might have hold equivalents as a discrete equivalent technique. We have these three classes. Today what we want to focus on is this first class, numerical integration approaches. Let's see what that means. And we've actually already done that or showed how this could arise. Here's the first class. Of discrete equivalent techniques. Here's our picture that we can keep in mind as we are trying to understand what we're doing. This blue line is a curve of x of t. That's just some function. And let's say this is our time axis, our independent variable. And this might be time little t. And this is time little t minus capital T. Where the difference now between those is this separation, capital T. That's our sampling period. This point right there is x of t, which we are actually going to go ahead and say t is little nt. Let me then erase that and say this is now going to be x of nt, since this is now what we're saying. That's where we're going to just say, oh, this t is now at the sample period n, capital T sample periods into time. This point is then one time sample before that, or this is the point x of n minus 1 times t. With numerical integration, what we're really wanting is to find a way to numerically compute the area underneath this curve x of t. And I've shaded this in two different colors because I want to now say that y of t is, well, let me say y of t is now the integral from 0 to t of x of tau d tau. Or we could now say that y of t is defined to be the area underneath this function that we just arbitrarily sketched, x of t, up to time t, and y of t minus capital T is the area under that same curve, but now not quite to t, but it's up to time little t minus capital T. Which, if we write an equation for y of little t in terms of y of little t minus capital T, they are the same as long as we add in this area underneath the curve x of t between t minus capital T and t. And we can write that or represent that as this integral from t minus capital T to t of x of tau d tau. If somebody gives us the area under that x of t curve at time t minus capital T, we'll call that y of t minus capital T. To get the next y of t, all we have to do is add in the small sliver or that additional piece underneath the x of t curve between t minus capital T and little t. Bless you. So if we now let t equal nt, we can now say that we have, maybe I shouldn't slide quite so much, we have y of little n capital T equal to y of little n minus 1 capital T plus the integral of nt minus t to nt x of tau d tau. And every one of these numerical integration strategies or techniques that we will talk about today all deal with how do we approximate that integral. How do we approximate the area underneath x of t? These different numerical integration techniques we're all allergic to these numerical integration techniques, apparently. It'll get better. Okay, so now we have different numerical integration techniques all based on this integral nt minus t to nt x of t. However, how do we approximate that? And how that's approximated will influence these different numerical integration techniques, which are just discrete equivalents. Let's look at the first one, and we'll call this, hopefully this terminology will be clear, we'll call this the forward rule of numerical integration. By that, what I'm meaning is we want to approximate the integral, and I hope you know what I mean by the integral. It's that little piece of the sliver. Approximate the integral with actually a rectangular area and here's where the terminology or the term comes from. Looking forward from the instant of time or the value x of n minus 1t at the time n minus 1t. Meaning now we are going to, when we look at this integral with the forward numerical integration technique, we are going to go back and say, okay, now what I'm interested in is taking this particular point, holding that constant, and now that's my rectangle that I'm going to use to approximate the area underneath that blue shaded area. It's the forward approach. I'm looking forward from time little t minus capital T. And what's the area of that rectangle? It's a good thing we did our geometry class, right? It's just that height, x of little n minus 1t, times the width, which is capital T. So that's easy to do that integral. Don't you wish you could do that when you're second semester calculus? Oh, the integral? Sure, I'll just do this. Find rectangles. That's really all you were doing anyway, but they didn't present it that way, did they? So now what we're saying is we have the width, that's capital T, times the height, and that's just x at time n minus 1 capital T. Which means then that when we want to do the numerical integration approach, we have y of little n capital T is approximately, because this is just an approximation, you can see that that flat top is not necessarily covering that x of t curve just exactly right. So y of nt is approximately what it was one sample period before, plus what we're approximating the area underneath that curve to be, which is now capital T times x of n minus 1t, or you could write that as nt minus t, however you want to think of that argument. But we said we want to figure out a way to go from an h of s to an h of z. Well, those are in the frequency domain. So let's take this time domain difference equation into the frequency domain and see if we can figure out a way to go from h of s to h of z. And this is the forward rule. So now, let's look at the transform domain. If we transform that difference equation, the z transform of little y of nt is just capital Y of z. And I'm going to get tired of doing that squiggly equality, but you know that this is really an approximation. What happens when I z transform y of little nt minus capital T in terms of capital Y of z? That's why we learned what we learned before, right? So that's easy. And now what does the next term present us with? Tz to the minus 1 capital X of z. Now we have an equation in the frequency domain that contains the input, capital X of z, and the output, capital Y of z. Let's solve that for a transfer function between x and y. Those were both capitals if you couldn't hear that in my description. Capital X to capital Y. So that's y, capital Y over capital Z. We have 1 minus z to the minus 1 y of z equaling t z to the minus 1 x of z. Whoops. But that now gives us this transfer function of t z to the minus 1 over 1 minus z to the minus 1. I don't like those z to the minus 1s, so let's either factor them out or multiply both top and bottom by z, and we end up with t over z minus 1. And that's what we're doing in the frequency domain for the discrete time representation of a discrete equivalent using the forward numerical integration approach. So what? Well, we need to find a way to go from S to Z. This is now something in the Z domain. Let's go back and remind ourselves what we had in the continuous time case. In the continuous time, our integral, let's say y of t, to find the area under the curve is simply this integral from 0 to t, x of tau d tau. But if we Laplace transform that, that's just 1 over s operating on the input, capital X of s. Now we have a way of comparing s and z. This is what happens in the s domain. That's what happens, whoops, that's a t, not a 1 up there if you're trying to see what's going on. We have t over z minus 1 in the z domain, and that's our correlation between the s and the z. If we compare those then, we now see that this 1 over s is consistent with, in the z domain, t over z minus 1. Well, it might be kind of weird always thinking in reciprocal terms or sense, so let's just invert both sides so that we now have a way of comparing s and z, or s is now this quantity z minus 1 over t. And that's now our way of finding a discrete equivalent using the forward numerical integration approach. Meaning, if I give you a transfer function, h of s, you now simply take that h of s, and everywhere you see an s, you substitute z minus 1 over t. And then you just clean it up, and now you have an h of z instead of an h of s. Pretty easy. Yes? So now this may not be quite what we want, but this makes a pretty clean and quick way. So the question was, is that going to underestimate the... What? So now a decreasing signal, is that going to overestimate? And that's what we had illustrated there. Our x of t was decreasing over that interval of time, and we were overestimating that. But the idea is capital T is going to be pretty slim, and maybe it will sort of average itself out if x of t has some shape to it beyond just monotonic. But we'll look at more issues somewhat related to that, but let's just look at what we can find doing this approach. But first, let me just tell you what I tried to say in words before. What we want to do to find an h of z from an h of s is replace s with z minus 1 over t in whatever transfer function somebody gives us, capital H of s, to actually obtain capital H of z. Let's do an example. Suppose I give you an h of s, which is a over s plus a. What is that? If I said this is a object in a ECE class, and it's in the form of a transfer function, and I hand it to you, and I say, what is this h of s? What are you going to tell me? It's a low-pass filter, isn't it? It's first order, and it's a low-pass filter. You should just see the Bode plot of that jumping out at you if you're ECE majors, right? That's a low-pass filter. In terms of the analog properties, where's the pole of this low-pass filter? That's the value of s that causes that denominator, or values of s that cause that denominator to vanish, and there's only one of those. That's the first order. So we have a pole at minus a. And in the s-plane, you could sketch this s-plane plot and put a pole at minus a. Do we have any finite zeros? Do we have any finite values of s that cause h of s to vanish? Do we have any infinite zeros? Yes. So we are going to have to start learning about infinite zeros in the next discrete equivalent topic of pole zero matching. So I'm going to try to get you comfortable with what we're meaning by finite zeros and infinite zeros. There is one infinite value of s that will cause h of s to go to 0. As s gets really, really big, h of s goes to 0. So we have one infinite zero because there's only an s to the 1 power downstairs. And we have no finite zeros. There's no finite value of s that causes h of s to vanish. Is that clear? So now we're going to be talking about finite zeros and infinite zeros. Yes? Negative infinity could be considered a zero, but we only have one of those. There's only one value of s. It's either plus infinity or minus infinity. They sort of meet up around this, let's say, point at infinity. We could think of it. But we only have one of those. The question was, is it minus infinity, plus infinity? There's only one s because s is raised to the first power. We only have one infinite zero, and we just really refer to it as a zero at infinity. We don't really distinguish whether it's positive or negative. It's just out there. Okay? But we have no finite zero in this transfer function. That clear? What's the DC gain? If you were sketching this Bode plot, where would you start that horizontal line? At what level vertically? DC is an omega that's not shaking, isn't it? Omega is 0, so S is 0. This is now A over A, or we have a DC gain of 1. We have a 0 dB for our constant flat piece until we reach the pole at minus A, which in frequency is at omega equal to A, and then it starts rolling off. And the roll-off rate is 20 dB per decade, or 6 dB per octave. An octave being a factor of 2. All right, so we feel warm and fuzzy about that transfer function, h of s. It's a low-pass filter, first order. Let's see what it looks like when we use the forward rule of numerical integration to find a discrete equivalent. Our forward rule to find h of z. And we're going to have a lot of these h's floating around, so let me put a subscript on this, h sub f, for the forward rule. That means that we're going to find that by looking at h of s when S now is replaced everywhere with what we said it was equal to, which is this z minus 1 over t. Well, that's pretty easy to do for this transfer function. That's just the S was in one place, and that one place was right there. So let me just put z minus 1 over t where S was. And if I wanted to, I could say, you know what, I can always multiply by 1, which is, in this case, I'm going to write 1 as capital T over capital T. That allows my h sub f of z to be a capital T z minus 1 plus at. Maybe I shouldn't have put that in parentheses. We just have z minus 1 plus at. What's this discrete transfer function look like? We could start talking about poles and zeros and gains, DC gains. Where's the pole? Do we have a pole? Do we have a finite pole? Do we have a finite value of z that causes that denominator to vanish? We simply set the denominator equal to 0 and evaluate for z. So this is now 1 minus at. Okay? And if a was, I don't know, minus, wait a minute, a is, let's say, 4. Let's say we had a low-pass filter with a bandwidth of 4 radians per second. We have a pole at minus 4 in the S-plane, but a itself is 4. We now have 1 minus 4 times whatever our sample period is. So that's going to be where? It's going to be somewhere on the real line in the z-plane. Less than 1. 1 minus some small piece, depending on what capital T is. That's where our pole is in h of z. What about our zeros? Do we have any finite zeros? This is looking kind of consistent with what we had before, right? We have one pole, and is it stable? Well, we don't know. It may depend on the choice of A and T. If we weren't choosing those, if we didn't choose T properly, we might have problems. What about the gain of this? What low frequency gain? Let's say the DC gain. How do we find that? Do we set z equal to 0? No, because S and Z are what? Z is equal to e to the st, isn't it? So if we set S equal to 0, Z is 1. Now, if we plug in Z equal to 1 to that transfer function, we get AT up top, and we get the same downstairs, don't we? A DC gain of 1. So we have consistency at low frequencies. We have a pole, one pole, no finite zeros. It seems like that's somewhat like h of s. It's now h of z. This is now a low-pass filter for a discrete time system, and you can find the difference equation for that very easily, can't you? You can now cross-multiply and find a difference equation relating x, the input, and y, the output. And now you have a way of finding difference equations instead of solving differential equations. Or instead of filtering with RLs and Cs or op amps in the lab, now you can find that equivalent in your computer and numerically create that filtered input waveform with a 12th order filter if you want. That's the forward rule. Let's look at B. We did A was the forward rule. Maybe we should have called it F, because now B is the backward rule. And I think you can anticipate what this is going to be. Now we're going to approximate that integral with the rectangular area looking backward from x of nt. Meaning now, if we have this integral of nt minus t to nt, x of tau d tau, we are approximating that. The width of that rectangle is still capital T, except now we're looking backwards from the time x of little n capital T. So that if we were back here somewhere, now we would be looking at that area. We are now looking backward from this point, little x of nt, and now we're underestimating for this particular picture. But we're hoping that capital T is not too big so that that small approximation is not that significant. Now we just repeat what we've done before. Now we can say, okay, y of little n capital T is approximately y of little nt minus t, one time step before, plus the area under that integral, which we're approximating with the backward rule, which is t x of nt. And what did we do to get this relationship between s and z? Now we transformed that difference equation to give us y of z is equal to z to the minus 1, y of z, plus t x of z. Or, getting this transfer function from x to y, which is y over x, is now this t over 1 minus z to the minus 1. Or, if I multiply both top and bottom by z, I now have tz over z minus 1. And if I compare the transforms again, I'm now comparing 1 over s to this tz over z minus 1, or if I reciprocate both, or take the inverse of both sides, I now am looking at s being z minus 1 over tz. And if somebody says, give me an h of z with the backward rule, now what you will do is you will replace s with this new formula, z minus 1 tz, in your given transfer function h of s to obtain h of z. Let's stick with the same example so that we can compare and contrast these. Our h of s was a over s plus a. And what we want to do now is use the backward rule. H sub b of z is now going to be h of s. And everywhere we have an s, we replace it with z minus 1 over tz. Or we need to filter that out, a over, using this low-pass filter, right? We just have to pick the right a value. So now we have a over z minus 1 tz plus a. And we don't really like ratios of ratios. Let's multiply by a convenient 1 value. Which gives us tz over tz. And we now have a tz over z minus 1 plus a tz. Or there is our h sub b of z. And do we feel okay with that as a way of approximating h of s? Are they even close? Do we have any poles? Just set the denominator equal to 0 and see what happens. Solve for z. And we get z is equal to 1 over that coefficient that's scaling z. So that we have a pole at 1 over 1 plus at. And if a was 4 and t was some value, that's going to be something less than 1, isn't it? 1 over a number bigger than 1. Well, that's nice. It means it's inside the unit circle. What about our 0? Do we have any finite zeros? We do now have a finite 0. It's at z equals 0. What about the DC gain? It's 1 again. Good. So we're okay, aren't we, with this approximation? And if I gave you this h sub b of z as a transfer function and said, go code this in your computer, you could give me the difference equation relating the input x and the output y, and now you have a way of filtering that input sequence x to generate a y, a first order filtered y. If you wanted to, yes? So in this transformation approach, for this particular transfer function, we've introduced a finite 0 when we didn't have one in the continuous time transfer function. That may or may not be an issue. But yes, we did introduce a finite 0 when we didn't start with one in the original h of s expression. That may be okay. That answer your question? I don't know if I repeated your question for the audience that's at home. They're not playing along with us, are they? Maybe I'll just not post this lecture. Question? So the question was, how do we pick our sampling period, capital T? Or what if we're not very clever or very, I don't want to use the word smart because we're all smart, and how would we pick capital T? How did we agree? What was the rule of thumb that we said we would use for capital T? 30 times the bandwidth. And we know what the bandwidth is, don't we? It's now out there at A. So now we know how to pick capital T. A is now 2 pi f, or it's 2 pi over capital T, and we could solve for T, well, that if we multiplied that by 30. Okay? So now we have our A. We would want to pick 2 pi f sub s to equal 30A. And f sub s is related to capital T. So now the question was, if I really want an accurate integration, I would pick capital T really, really small. All right? If you pick capital T really, really small, whatever A is, this is going to be bigger than 1, isn't it? So we're going to be slightly inside the unit circle. But what does that tell you? That just tells you that between sample periods, between 0 and capital T, we're not moving very much, but T is very, very small, so we shouldn't be moving very much. So the smaller you make capital T, the closer that pole is to the unit circle, which is really consistent with what's happening. You're not asking to change much between sample periods. And if you make capital T larger, then your pole will be further into the unit circle, and you will be changing more between sample periods. Is that okay? Did I see another question? I think it shouldn't be too big of a deal right now. We just are looking at different ways of finding discrete equivalents for, and in our example, it's just a first order. And we'll talk more about stability of these. We'll actually learn that the backward rule is better in terms of stability properties than the forward rule. If we start with a stable transfer function, we will get a stable h of z in the backward approach. We're not guaranteed of that in the forward approach. Let's look at one more. And this is just because I like to say it. Let's look at the trapezoid rule. Maybe somebody's saying, I don't like that flat top. Right? I want to see a little slope to that, which means now we're just averaging the two heights, x. And that's our trapezoid rule. What we want to do now is approximate the integral by a trapezoid. Which means now if we're integrating from little nt, or little n capital T minus capital T to little n capital T, x of tau, d tau, now what we're saying is the width is still capital T, but now let's take the average of the right side and the left side of that rectangle. And now we've got a trapezoid. So that now we have x of nt plus x of nt minus t over 2. And really, one way of thinking of this, if you wanted to, we're basically averaging the forward and the backward approach that we just did. So we're doing F and B, averaging F and B, forward and backward. Meaning, now we have our difference equation, y of little nt is now y of little n capital T minus capital T plus t over 2 x of nt plus x of nt minus t. And maybe you've heard of this as the bilinear transformation. You may hear it many different ways in the literature. If we take this through the transform or into the transform domain, now what do we have? We now have y of z, capital Y of z, is equal to z to the minus 1, capital Y of z, plus t over 2, that's just a factor, 1 plus z to the minus 1, capital X of z, combining those terms and factoring out the common X of z. And now if I find this transfer function between X and Y, my denominator is just 1 minus z inverse. Since I'm just pulling that z to the minus 1 y of z over, and my numerator is just what's scaling capital X of z. And that's this t over 2, 1 plus z to the minus 1. Or if we multiply by 1 again, which is z over z, we now have t over 2, z plus 1 over z minus 1. And maybe you'll see this t over 2 pulled out front. And if we compare these transforms, S and Z, we're now looking at 1 over S being the same or equivalent to t over 2, z plus 1 over z minus 1, or S is now the reciprocal of that top line. It's now 2 over cap t, z minus 1 over z plus 1. And to find this discrete equivalent using the bilinear transformation or this trapezoidal rule of numerical integration, we simply replace S with this 2 over t z minus 1 over z plus 1 in h of s to obtain h of z. Now we need to do our example with this trapezoid rule and keep the same low-pass filter with a bandwidth of A. We can now say h sub t of z is simply found from h of s if we replace s everywhere with whatever we said it was supposed to equal, this 2 over t z minus 1 over z plus 1. So that now we have an a over 2 over t z minus 1 z plus 1 plus a, and we can multiply by our favorite 1, which in this case might be t times the quantity z plus 1 over t times the quantity z plus 1, or something to that effect. And we have a t z plus 1, 2 z minus 1 plus a t z plus 1. Or if we collect like terms, we now can pull out and say we have 2 plus AT scaling Z, and we have AT minus 2 as our constant term, and upstairs we have AT Z plus 1. And that's now our discrete equivalent using the trapezoidal numerical integration approach. Where is our pole? And how many poles do we have? We simply solve for z in the denominator when we set the denominator equal to 0, and we now have, let's say, the negative of that constant coefficient divided by the factor scaling z, and that gives us this 2 minus AT over 2 plus AT. Do we have a finite zero? Now it's at minus 1. The last one was at 0. We can kind of argue that those 2 points in the z-plane are sort of like infinite, because the imaginary axis maps to the unit circle, and we just go from 1 to minus 1. Minus 1 sort of looks like infinity. If we were looking at a pole on the real axis in the z-plane, it's really slow at z equal to 1, and it gets really, really fast as we get closer to the origin. So z equals 0 could also be thought of sort of like a point at infinity in the z-plane. But here, this discrete equivalent is saying our 0 is at minus 1. What about our DC gain? Now we plug in z to this mess right here, and we get 2 upstairs times AT. Downstairs we get 2 and a minus 2, and plus AT plus AT, or 2AT, and we get our DC gain back. Questions on those 3 discrete equivalent approaches. 3 different numerical integration strategies, all based on different ways of approximating the area under that little piece of x of t, either forward, backward, or trapezoidal. Right? So we're either flat forward, flat backward, or we are slanting, sloping, averaging those 2 points. I've already hinted a little bit at this next question. Is stability always preserved with numerical integration? And if you were paying attention earlier, I think I have already answered that question. It depends, right? It depends on the numerical integration approach. Let's now check the mapping. From the S-plane to the Z-plane for these different numerical integration techniques. Let's look at the forward rule. We said in that particular case we were replacing S with z minus 1 over t. Well, let's look at the other way around. We know what's stable in the S-plane. We know it's the whole complex S-plane, or left half of the complex S-plane. Everything to the left of the imaginary axis. That's stable in the S-plane. So let's see if we can map from the S-plane into the Z-plane. So let's solve this relationship for Z in terms of S. If we equated those and solved for Z, multiply through by capital T and add 1, so we have 1 plus TS or ST. Well, what does that give us? If we look at what we have, here is our S-plane, and we're saying that this is our stable region. Now, we want to map that stable region through this mapping. Z is equal to 1 plus TS. Now, I'm going to have to make my paper wider. Sorry. What does that do to every point in the S-plane? Well, first it just translates at 1, doesn't it? So it just shifts it to the right 1, which means that I could come over here and go, oh, there's 1. There's my Z-plane. And it's just going to be scaling S by T, but that's basically, whoops, I like a different color. Ooh, what's that say? Where's our stability region in the Z-plane? Do you see any shaded region in the Z-plane that lies outside our stable region in the Z-plane? Yeah. So we're not guaranteed of starting with a stable H of S and producing a stable H of Z with the forward numerical integration approach. What I'm trying to then illustrate here is that if we started with a stable H of S, we are not guaranteed of H of Z being stable. Okay? And you could play with this and look, not that this would be a good choice, but somebody was arguing that maybe we didn't have a good choice for capital T before. If I started with a point, let's say minus 4 plus J 0.1 in the S-plane, and suppose that somebody hadn't taken this class and they just said, oh, let's sample at 500 milliseconds, or every half a second. Let's take a sample. Maybe that's not a good choice, but what does that do? Maybe it doesn't matter whether it's good or bad. We just want to see, is it possible to be bad in using this mapping? We know Z is 1 plus TS. Whoa, what am I doing? I got a little bit crazy with my addition. So 1 plus TS is equal to 1 plus T times S, or this is now 1 minus 2 plus J, what, 0.05? Where's that bad boy? He's outside the unit circle, isn't he? So we're unstable. Now, it's possible to show that for the backward and the trapezoid, they actually produce stable results. So for the backward rule, I'm not going to go through it because I'm running out of time, but you can show that the stable region in the S-plane, which is the entire left half side, actually maps into, I wish I could sketch better, but it maps into this location in the z-plane. That's the backward rule. That's this, when we replace s everywhere with z minus 1 over tz. The trapezoid rule anybody want to guess what it does when you map? There's our unit circle. If you looked at what it does, it maps the stable region into the whole stable region in the z-plane. Here is our z-plane, meaning it doesn't restrict to a much tighter region. It actually maps from one stable to the complete stable region in the z-plane. And I'm not sure I'm going to show that, but you can just see that you now have two ways of producing stable transformations going from h of s to h of z with numerical integration. And I may give you another virtual. We'll see. Lecture, that is. So stay tuned.